Welcome back to chapter 11. We made it through the linear algebra part and we are now going to slowly turn towards developing multivariable calculus, which will cover basically the rest of the semester, roughly. Maybe a bit of ODEs in the end, ordinary differential equations, but we'll see about that. First of all, the important thing is to develop this general calculus methods. As you've seen in the last semester, we started very basic. We had set theory and so on. Then we discussed convergence of sequences. And by sequences, I mean sequences in the real numbers or in the complex numbers. Those were the cases we've treated so far. We've established methods for convergence. We studied sequences in series and so on, and then formulated continuity also for functions between, from subsets of fields. So in the field usually of real and complex numbers, but we had formulated most things for general fields, but the real and complex numbers were the interesting ones for us. Now, then we developed differentiability and so on, the notion of derivative, but in doing so, we always used all the time in the methods that we used to prove the results about derivatives and so on, we used convergence of sequences and we always used continuity and the results from the chapters before. If we want to do the same in the higher dimensional case, so let's say we want to develop calculus for maps from Rn to Rm, so between any dimensions. So for them we want to develop derivatives and so on. We will need linear algebra for that. So as I tried to kind of imprint in your brain in the last semester, taking derivatives and deriving functions means approximating them by something linear. We had kind of in the one-dimensional situation, we had kind of the tangent lines to a graph. This was this linear approximation. And we will do the same thing here now with linear maps. So this is where we need the linear algebra that we studied so far, but more on this later. Before we come to that, so in order to do so, we need a general way of dealing with convergence of continuity and a generalization of the methods from the previous semester. So in this chapter, we will just do just that. Namely, we want to study convergence and continuity in so-called metric spaces. These metric spaces are kind of the, not the most general, but a very general setting and a very flexible setting of to formulate convergence and continuity in a way that directly generalizes the situation from the previous semester where we did this for numbers. So in the first section, I want to focus on the convergence case. Namely, I first want to introduce metric spaces and discuss them and show that what the general idea here is, and also where it connects to linear algebra, as we did before. So there's a direct connection to chapter 10, as we shall see in a bit. And we will study convergence and see kind of that metric spaces allow to a general convergence definition, which is actually almost precisely the same as for numbers. And I think if you understood convergence for numbers, you just have to take this one step of abstraction. But it turns out that the proofs we will see here are all one-by-one analogs of the ones for numbers before. So don't be afraid if this looks very abstract to you and if this kind of set theoretic discussions and so on looks weird. It is not that difficult. It's really not that hard once you get the grasp of it and once you get the main idea. And always keep in mind kind of what you thought about or what your intuition was about sequences of numbers and so on. And you will really see that this is really straightforward generalization of this. Now, as a bit of motivation for metric spaces. So what do we actually need? So what would be the minimum requirement to formulate something like convergence? Convergence makes a statement about numbers approximating a certain value, so coming closer and closer and closer to a certain value, and there's already the point. On an arbitrary set, I have no notion of being close, so this saying that two elements are close to each other, so far this makes no sense, so there's nothing, what should this be? So we need a general framework to formulate these notions of closeness and to see kind of how we can measure closeness. And to do so, let's think back about the last semester and how we measured closeness there. So we said something approximated or some numbers were close, and usually we had a condition looking a bit like this. We said that two numbers in like real or complex numbers were close, or this was our interpretation of this, when kind of x and y, if those are numbers, if the absolute value of these of the difference of those two is smaller than a certain epsilon. Yes, the epsilon is back in this semester, and it will, in this chapter, and it will be back for the rest of the semester. So this kind of, if epsilon was small, this was our expression of something being close. That was the idea. And when we studied convergence and so on, we had funny proofs where we had assumed something is smaller than epsilon over 3, then we did some magic with inequalities and something turned out to be smaller than epsilon and so on. So there were a lot of tricks by this, but we basically used tricks or used methods where we kind of used the absolute value and used methods that work both in the real and the complex case, because basically all we need was some elementary properties of the absolute value. Let me take that away here so in order not to distract us. So what were properties of the absolute value that we needed? Let me just list a few of them. The absolute value had some properties which were useful, namely, we had seen that kind of if the absolute value of something goes to 0, then the term inside goes to, must go to 0 as well. This is kind of how we show that if the absolute value of xn minus a, something went to 0, this shows the convergence of xn to a. So this is a property that we need. And so the first crucial property, or what we really need to do this then, is first of all that the absolute value is of some number x is bigger than or equal to 0. This is what we also needed because we always have some estimate from below, and so if we could estimate an absolute value from above, we could get some general upper and lower bounds. And we have seen that the absolute value is 0 if and only if x is equal to 0. Secondly, something we also needed, and that's kind of important, is that the absolute value of minus x, if we just take a minus in front, this is the same as the absolute value of x. So this is also easy to see, so obvious for all x in k. Here, this is also here for all x in k, where k is now the real of the complex numbers, or more generally any field with an absolute value. But in the real of the complex numbers, we have this absolute value, and so this always holds. And this means, in particular, it has some consequence. We always had absolute values of differences, x minus y. And since this minus doesn't change it, this is always the same as y minus x to the absolute value for all x, y in k. Okay, so this doesn't matter, so which row of them? So the distance, this would be kind of some measure of the distance of x and y. Third thing that was extremely important when we had this absurd chains of inequalities sometimes, that the absolute value of x plus y is smaller than or equal to the absolute value of x plus the one of y, the triangle inequality. Okay. Now, if we study those differences, we use this often in the form, in particular, if we have x plus y to the absolute value, we could write this as, this is something we did loads of times, x minus z plus z minus y, and use the triangle inequality to estimate this from above by x minus z plus z minus y to the absolute value. So this is a special case. So this is a minus. So kind of this is the distance between x and y. This should be the distance between x and z, and the one between z and y. And a motivated to drawing a triangle and so on. So the distance between these two is smaller than the distances that we get if we take a detour via some point z. This was the idea here. And it turns out if we generalize these properties, many of the convergence statements we had so far can be straightforward generalized to this notion of metric spaces without any other proofs. So we basically need to do the same proofs and just replace this absolute value by something more general. And this something is what I'm going to define now. This is the so-called metric. Namely, we want to formalize this notion of the distance of 2 points. So the distance of 2 points in the field was this absolute value of the difference. So let's see how we can do this. So let X be a set, some arbitrary set. A metric, a map is called a metric, so a map D, so this should be this is what we call a metric, and this should be a distance function, so which associates distances. So what we need is 2 points, so the input is x times x, and this should spit out the distance between those points, and the distance we always see as a real number. Such a map is called metric on x or distance function. On x if it has the following properties. So we want to generalize these statements in so far as, first of all, this statement is also called positive definiteness. This property, not this statement. Positive definiteness. Namely, we want that first of all, the distance between 2 points is always non-negative, which makes sense if it's a distance. So just intuitively for all x, y, and x. And we want that the distance between x and y is 0. So what should 0 distance mean? This should mean they are the same point, because no 2 points which are kind of not the same should have distance 0. This makes no sense. So it's 0 if and only if the points are the same, and otherwise it's positive. Okay, and this is kind of mimicking this property here. If you imagine we put in differences here, this would mean that the absolute value of a difference x minus y is 0 if and only if x minus y is 0, meaning x is equal to y. Okay, so the second property here, this was also some distance between x and y, and this looks a bit like a symmetry property, and this is the way we generalize this. To symmetry of a metric, the distance from x to y should be the same as the distance from y to x. This makes absolute sense, because distances shouldn't now depend on the order. For all x, y, and x. Okay, and as you see, this is the generalization of this. So finally, we need the triangle inequality. And there we want to, the analog of this, because this we can also see here as measuring distances. And so let's demand this as a property of the map we are studying. The triangle inequality. Whoops. So we want the distance from x to y is smaller than the sum of the distances from x to z plus the distance from z to y, so taking a detour via z for all x, y, and z in x. So just drawing the triangle here, so we have a point x and we have a point y, and the distance between the two would be the length of such a line segment here. And if we would take a detour via some point z, which might be anywhere, so we would get that this would be the distance from x to z, this would be the one from z to y, and the sum of the lengths of these two segments is bigger than or equal to this here. In fact, it's only equal, so here you might think, okay, it's strictly bigger, where should it be equal? It would be equal if z would be lying on this line. So if z would be somewhere here, then we would have, of course, an equality there. But as you see, this is also a straightforward generalization of this. Okay, so much for that. And of course, one more thing I'd like to, there's a triangle in the way, let me erase that. And finally, so this is called a metric. And the pair of x and the metric D is then called a metric space. So this explains the headline. This is the most general way of measuring distances and so on, and to formulate here, and not the most general, but a very general way to formulate convergence and so on. Okay, this is called a metric space. One often just doesn't write the metric in the notation. One often writes x for xd. So just in case the metric is obvious, it's clear it's referring to, we don't write this every single time. We will later on see a standard metric for r to the n, for example, and we will not always write the metric, but it's always clear which one we are taking there. Okay, so much for that. So we've generalized that. And now, of course, we're going to see examples. And before I give you some explicit examples, I want to give you a theorem which contains a lot of examples, because, so this was kind of, okay, nice and well done. So this was the absolute value, and we saw that this kind of defines a metric. So absolute value, if we take the absolute value of the difference, this defines a metric in this sense here on the real numbers or the complex numbers. But if you take a look at these properties here, there was a larger class of maps we could use, namely norms. These properties, if we would now replace the vertical bars by double bars, this is the triangle inequality for norms. This is a consequence of the norm property that kind of, with constants multiply on the outside with the absolute value, and this was property 1 of a norm. So norms give metrics. So this direct generalization of this absolute value, we get norms. So let me formulate this here as a mixture of theorem and definition again. 11.2. So let V with a norm be a normed vector space. Be a normed vector space. This can be real or complex, this doesn't matter. And keep in mind, so here we really work on a vector space, but in general for a metric X can be some set. So there's no requirement of this to be a vector space or anything. So then we can define a metric, namely D from V times V to R, dx y, and now let's mimic the absolute value construction, should be the norm of x minus y. Then this is a distance function. So this is a metric on V. This is the theorem part, and now for the definition part, this metric is then called the metric induced by the norm. So by the norm, double bars. Okay, called the metric induced by this norm. Okay, this is the general construction. This is how we can get a norm, and the absolute value is like a norm on C or on R, so this is actually a special case of this. So whenever we have a norm, and just geometrically keep in mind, so if you have two vectors x and y, this vector x minus y is the difference vector, so the vector connecting those two. So what the norm does is to measure the length of the difference vector. This is what the norm does, and so in this way geometrically also generalizes what we consider as distance and of length. Okay, so let's prove this. So we've basically already done all this, but let me do this once in detail. But property one of norms, it holds that d of xy, which is the norm of x minus y, is always non-negative. This was straightforward in this property of a norm for all x, y in V. And norm of x minus y is 0 if and only if x minus y is 0, if and only if x equals y. So, D has property 1, and now I mean, of course, property of a metric, which is satisfied here. Okay, the symmetry is easy. So, by property 2 of norms, this was the property of scalar multiplication and putting this outside with the absolute value. We get that, let me do this here. D of xy, it's by definition the norm of x minus y. This is the same as the norm of minus y minus x. This is just playing around with the vectors. Now, this is just by this norm property, so this is minus 1 times this, so the result is the absolute value of minus 1 times the norm of y minus x, and this is, of course, 1. So this is the norm of y minus x, and by definition of this metric, this is d of y comma x, and this holds for all x, y in V. So D has property 2 as well. And for property 3, we need the property 3 of norms, namely the triangle inequality for norms. And this is basically the step I've already done there. So let's check. If we take two elements x and y, so the distance is x minus y. And now we just subtract and add a third vector at the same time. So this is the norm of x minus z plus z minus y. This is the sum of two vectors, and the triangle inequality for norms simply also says that the same inequality as for the absolute value holds, namely this is smaller than or equal to the norm of x minus z plus the norm of z minus y. And by definition of this function of the map D, this is d of xy, d of xz plus d of zy for all x, y, z in V. So D has property 3, namely the triangle inequality for metrics. And this shows that this is indeed a metric. So, important to keep in mind and not mix up, every norm induces a metric on the vector space, but not every metric space is coming from a norm. So this is just important to keep in mind. We can just define arbitrary metrics on sets by just having these properties, and there's no need for X to be a vector space or something. Okay, let me erase and then we'll see some explicit examples. Let's consider some very basic examples. So first of all, we've seen that norms induce metrics, and I want to write at least once down this most explicitly the most important metric that we use, namely the standard metric in Rn, which is the following. So the metric on Rn, just formally the metric on Rn induced by the Euclidean norm, and this is the norm you saw in the last chapter, by the Euclidean norm, and this means d from Rn times Rn to R. So d of x y is the norm, the standard norm, now the Euclidean norm of x minus y. And in the components, this reads as the square root of the sum of the squares, namely the sum from I equals 1 to n of xi minus yi squared. And this for all x equals x1 to xn and y equals y1 to yn in Rn. So this metric is called the Euclidean metric. On Rn. And whenever we talk about Rn, and don't mention explicitly a metric, we always refer to this one, because this is the most important one. This is the one that also from geometry, from lengths, and so on. This is that is really the distance that we would measure in R2 by a ruler or something. Or so this is the distance that we really need in Rn. Okay, this is the most general, and this is only a special case of what we did before. Now, as I do always when I do examples, I give you a stupid example. Namely, on each set X, there is a metric. There exists a metric. For example, a very stupid one, namely, now you might expect I would say, okay, everything goes to 0, but this is not allowed. This is not allowed by property 1, only 2 points, if you have the same point twice, this may go to 0, the rest must be not equal to 0, so I need to put in a little more effort, but there's a very stupid metric as well, namely d0 from x times x to r, and d0 does just the most elementary thing you could do. d0 of xy is either 1 or 0, and it's 1 if the points are not the same, and 0 if x is equal to y, if they are the same. So I don't want to prove the details about this, but you can see it's a metric. I mean, first of all, it's only 0 if the points are the same by definition. Second property, the symmetry. So if x is not equal to y, then y is not equal to x. So in both cases, it would be 1. Fine. And the triangle inequality, there we would just have, they have to make a case distinction, but on the left-hand side, it's 0 or 1, and on the right-hand side, it's 1 or 2, depending on which case comes out, but this is always satisfied. So this is something that's easy to check. So D0 is called the discrete metric on X. I would have to elaborate a lot more about metric spaces to explain this name, so let's keep it at that. So it's just the name discrete metric. Okay, and one more example how you can get new metric spaces from old ones, and this is something which doesn't work for norms in general. So if xd is a metric space. So assume we have already a given space, and we take an arbitrary subset of X, then A with a restricted metric is also a metric space. Where dA is just the restriction of the metric to points in A. So the restriction of D to A cross A as a map from A cross A to R. And there it obviously follows from the metric properties that this has the metric properties as well, so this is, there's nothing to prove. And this is now good news, because this doesn't work for norms, of course, because norms are only defined on vector spaces, so if you take a subset of a norm vector space, which is not the vector space itself, the term norm doesn't make any sense. So metrics really go down to subsets, while norms or other constructions might not. Okay, so next up, we want to formulate this general definition of convergence. So let's do that. Definition 1.11.4. So assume we have a metric space. Assume we have a sequence in X, n in n, sequence in X, and we have some element A in X. And now we want to formulate the condition that the sequence xn goes to the point A. So let's maybe think back to last semester. So what was convergence? Convergence, if we had a sequence, this time the real numbers or the complex numbers, we had this condition that for all epsilon bigger than 0, and if you couldn't write down the definition now, if I would really ask you now to write down this definition, please, please, please study, because this is so important. So for each epsilon bigger than 0, there exists some n0 in n, such that the distance, so xn minus a to the absolute value, is smaller than epsilon for all n bigger than n0. And if we now take a look at this and on our new knowledge about metric spaces, it's kind of almost immediate how to generalize this, because this is now a special case of our notion of distance of a metric. So if we have a metric space, we generalize it in the same way. So we say that xn, the sequence, converges to A if, and now I would, if I had an audience, I would now ask you what I should write now, because now it's, if you understood what we did here with the distance functions, you should now see what happens. For all epsilon bigger than 0, there exists some n0 in n such that the distance of xn and a is smaller than epsilon for all n bigger than n0. So this generalizes really the notion of convergence, and I hope you really, and it's really important that you understood the notion of convergence from the last term. So for every small neighborhood of our point A, so everything, so if we take some epsilon, only numbers which are epsilon close to there, we had that almost all elements, so from a certain element on, from this n0 on, everything is in this small range around the point. And this is precisely the same. Here we say the distance from xn to a should be so small, epsilon small, and that this is always in this small area where the distance is so small from the n0th term on. So this is a straightforward generalization. And of course we generalize the rest as well. So this is convergence to a point, and we say that xn, we call a sequence just convergent if it converges to some element, to some a in x, and we call the sequence divergent if it's not convergent. This is also just taken from the real and complex numbers. So this is divergent if it is not convergent. Okay, so you don't need to learn new terminology, you just apply the old one to the new situation here. So this is convergence and divergence, and let me erase the reminder here, so to get some space for this here. And of course, at this point, we have this formal definition, but it's of course a question, and I'm sure that no one remembers because I wouldn't either. Which properties are now automatically follow from this convergence definition, or which theorems and which results can trace back or not? For example, here it makes no sense to say that the sum of sequences converges because we don't have a sum. There's no x. In vector space it would turn out it will, but so far we don't know anything there. I'm sorry, I was a little bit fast. I forgot one more piece of notation, but it's old notation, namely if xn converges to A, then we also take the same terminology as before, namely we call A the limit of the sequence xn, and write lim n to infinity of xn equals A, just as we did for numbers here. So, I mean, this is now this very general convergence definition. So now we can say, since this includes the case of normed vector spaces, now in every normed vector space we could possibly imagine, we can now formulate what convergence means. And of course for general metric spaces as well, and we will maybe later see more of them. But let me just mention, I don't want to go too much into detail with examples about abstract metric spaces because this is not too relevant for us. I'm streamlining this a bit towards our development of higher dimensional calculus and leaving some things aside that are not too relevant for you. Okay, so two things collected in a remark. Namely, first of all, the normed vector space. This is kind of the most important case also for what you're doing. So I want to once explicitly write down the convergence there. So there it even looks even more similar to the old definition. If V is a normed vector space, and which we consider as a metric space with the induced metric, then a sequence xn and in n, which is now a sequence in V, which converges to some A in V, if the following holds. So here, just take a look at the definition here. So the only difference is that here the distance function is now the one given by the norm. So let's write down explicitly for all epsilon bigger than 0, there exists an n0 in n, such that the norm of the difference, so xn minus A, is smaller than epsilon for all n bigger than or equal to n0. And this is just the same as we had in the last semester, except that we had one vertical bar on each side instead of two. So this is really, it can't get more similar than that. Secondly, one checks from the definition of convergence, there's some nice property that, so if you're in an arbitrary metric space, and we have a sequence in the metric space, sequence in X, then we could basically also formulate this for in terms of the convergence we had before, and we actually don't need a new convergence term, but this would make some computations quite awkward. But it turns out that the sequence xn, this converges to some element A of the metric space, if and only if the sequence of distances, so the sequence dxn to A, if this as a sequence, this is now a sequence of real numbers. So if this converges to 0 in the real numbers. So technically this convergence is actually the old convergence. This is precisely what we did last term. And from the metric properties, especially the non-negativity, you can really show that this is an equivalence, which I shall not do here, but this is another way of viewing convergence here. Now, I already said that some properties of, we had a lot of properties for convergence of real numbers, and some of them don't make sense, like the addition of sequences in general or something. But some things need to be carried on, which one might think are automatically true, but you need to reprove them here in this setting, but I will not do every single detail of them. So, in this case, Theorem 11.6, let XD be a metric space then the limit of a convergent sequence is unique. Nothing can converge against two separate values. This is what we've proven explicitly also for real numbers and complex numbers, and it turns out the proof is precisely the same. You just have to replace the difference of the absolute values by the metric. But everything goes through because we only need these elementary properties that are sketched in the beginning, and so everything is proven the same way. And so I'm carrying this out in the lecture notes, but it's basically also, I literally only copy-pasted the old proof and replaced the absolute values by the distance. So this is in the lecture notes, this is something, but talking about limits, this is important to know. So this is something you should keep in mind. Now, before going on, we want to deal with our most important case, so with the most interesting case of convergence, namely Theorem 11.7. So we consider k and n, and we consider r to the k with Euclidean metric. This is the case in which we want to develop calculus, so this is where we need convergence the most. Now, if we take a sequence in Rk, we of course have the different components. So we have, if we take xn as a sequence, so let me write down, so that xn be a sequence in Rk, and of course we can write all these elements as k tuples of real numbers just by construction. So let xn be x1n, x2n, and so on to xkn in Rk for all n in n. Okay, and we have some point A, which is then in coordinates a1 to ak in Rk, which should be our limit. Now, we have, of course, several ways of looking at convergence. So we can use this abstract definition of convergence, but of course there's something which is kind of quite immediate, namely we could just take the coordinate sequences. We could just take the sequence x1n itself, see if it converges to a1. We can then take x2n, see if it converges to a2, and so on. So a priori, this would be a different notion of convergence. So this is somehow more natural, because this is something we can compute. We don't have to work with these abstract metrics and so on. This is weird. And the good news is, we don't have to decide, it's the same. Namely, then xn converges to A if and only if all the coordinate sequences xin converge to ai, to the corresponding coordinate of the limit point, for all I in 1 to n. And this is an extremely useful statement. This is what we need to really do computations about Rn. Let me quickly erase and then we'll prove. Okay, the one direction. We assume that it converges in the new sense, so the sequence converges in Rn with respect to this metric space convergence, and we want to show that the coordinate functions coordinate sequences converge. So before we do this, we make one assumption, and now it's again back to proofs with inequalities and epsilons and so on. So yeah, I'm enthusiastic, as you can maybe tell. So for some I between 1 and k and n in n, we compute, and we now make a beautiful estimate. So if we want to show the convergence of the coordinate sequences, we need to kind of discuss these sequences here, this difference here. So xin minus ai, so to the absolute value, these are the ones which have to become small in the old convergence sense. Now let's write this unnecessarily complicated, namely this is the same as the square root of xin minus ai squared. Okay, just definitely mean this property of the absolute value. Now we can just enhance this and add more non-negative summons, because this doesn't change, or this only changes this to the above, because roots are strictly monotonically increasing, as we've seen. monotonic increasing is enough here. Namely, this is smaller than or equal to the square root of, and now let's add the whole party, the sum j from 1 to n, x j n minus a j squared, sorry. So let's take this, and this is now by definition just the Euclidean metric. This is namely the difference of xn minus a in the Euclidean norm, which is d of xn a in the Euclidean metric. So this distance here is smaller than or equal to this one, and so since, if we now take an epsilon bigger than 0, by assumption, we know that xn converges. So by assumption, there exists n0 in n, such that d of xn a is smaller than epsilon for all n bigger than or equal to n0. But then, if we consider this estimate, if we call this star, if I just apply that, this of course means, since this is smaller than or equal to, xin minus ai is also smaller than or equal to this, so it's particularly smaller than epsilon for all n bigger than or equal to n0 and for all I in 1 to n. So if we take a particular coefficient sequence here, a coordinate sequence xin, we've seen that we can always, for every epsilon, we can find an n0. We can in fact take the same n0 for each I to make this convergent. So here it directly follows that xin n in n converges to ai for all I between 1 and, sorry, not nk, to k. Here it's also k. Sorry, I mixed up n and k here several times. Anywhere else? No, I think we're good. Yeah, okay. So this converges there, so this follows, this shows that part. Now for the other direction, so we assume that all these coordinate or coefficient sequences converge. I want to show that the big thing then converges in the Euclidean metric. Now, for this purpose, whoops, I took, sorry, I forgot the sheet, so I have to do this, I have to memorize that. Yeah, so it should be fine. Now, let epsilon be bigger than 0. Then, for each I, since they converge, so for each I between 1 and k, so there exists an ni in n such that xin minus ai to the absolute value is smaller than, and now I do a nice trick that we do all the time, epsilon divided by the square root of k. Yes, one of these proofs again. So that this holds for all n bigger than or equal to ni. Okay. Now, for each I, we can find an individual I, and just to have a common I, such that this holds for all I at the same time, we just take the biggest. Namely, put n0 to be the maximum of n1, n2, and so on to nk. Oops, running out of chalk. So if this is the biggest, then we can compute for all n bigger than n0 using these inequalities here, which I call double star now. We compute the following: d of xna, and this is the guy that needs to become small if we want convergence of the sequence x. This is the square root, Euclidean norm of x, sorry, I would use again n, this was correct this time, sorry, xn minus a to the Euclidean norm. This is the square root of the sum from 1 to k, no, I'm correct, xj, not ji, sorry, just to make this match with before, xin minus ai squared. And now again by the monotonicity of roots and by these inequalities here, so roots are strictly monotonic. So if I now apply this here and in the denominator, in the argument of the root here, I make the argument bigger, and so also the root becomes strictly bigger. So this is by strict monotonicity. There's this inequality, if I now insert double star, that each of these squares is now bounded from above by epsilon over square root of k squared, meaning this is smaller than the root sum I from 1 to n. And now we have epsilon squared over k, and this is again a k, sorry. So this is now the sum of k times this. This is of course constant, so not depending on the index, I want to say. So this is the square root of k times epsilon squared over k, which is the square root of epsilon squared, and this is epsilon, since epsilon is positive. So we have found an n0 in n such that for all n bigger than or equal to n0, the distance of n from xn to a is smaller than epsilon, and this shows the convergence. So as epsilon was arbitrary, xn, n in n converges to a, which shows the claim. Okay, now I have to stop at this point in the middle of the blackboards because I have an appointment now and I have to leave, so I'm running out of time. But we'll continue straight there next time. So now, cut.